Okay, so this kind of set of slides is just an introduction to information visualization. Generally, my slides are put together not necessarily by chapters in the book, if you're using the textbook. And then you would notice that the first ones, I kind of stick with the textbook more. So like maybe chapter 1 and 2 and 3 in the textbook, we're sticking to it a little bit more. And after that, I kind of diverge. But even for those, it may be that they only have 2 paragraphs in the textbook, and I have maybe a whole set of slides about it, like 20 or 30 slides. So I'm not following the textbook that closely, but I figure people need a different reading other than just the slides and the recording. And again, the recording, I understand, takes time to listen to it. So this set of slides just kind of give you an overview. So we'll start with some sample problems that I found that, you will see that some of them are not even colored. Not actually, none of them are colored. So don't even use color for them. And then kind of introduction about types of visualization, how does it work, and then some very basic structures about data and graphical. Basically, how do a lot of these visualization tools, and even they kind of have the same flavor as statistical tools, expect your data to be in. So I'll cover that a little bit at the very basic level, so you have something to kind of go forward with. Okay, so here is a game. There's color, but we're not going to use it necessarily. So let's say I have 9 numbers like that, like those, and I have 2 players playing them, and each can pick a number in turn of what's left, and they keep it. It's their number. So some player may keep number 6 and put it in their, on their side. Then player number 2 then needs to pick whatever is left. Cannot pick 6. So let's say they take 2. So now 2 and 6 are gone. Each player has them. And then player 1 comes back and he needs to pick something. So let's say I pick a 4. So now player 1 has a 6 and a 4, and player 2 only has a 2. And then they could go ahead and pick a 9. And the whole point is to reach 3 of these stones. I can have more than 3. But if I have 3 of them whose sum is 15, I win the game. And obviously that's, am I playing my opponent? I want to make sure that if there's one of these pieces that would move them to 15, I want to make sure I take it, so they don't get to get the sum of 15. Okay, so that's a game. How can visualization help with it? I'll skip 2 slides. In person, if everybody was in class, we could have even played it. And you see, I would have won, or I would not have lost ever. But here's this one solution for it, is to actually play tic-tac-toe. And how is that possible? Well, there's this idea of magic squares. So a magic square has the exact sum on each row, column, and diagonal. So if you sum them up, like 6, 1, and 8 is 15, all of these are 15. Okay, so if I were to play that game, really, I can use this visual structure. And again, I told you, it's not even black, it's black and white. It doesn't even have much graphics. Now, I can make it interactive with graphics, and I can start, like I said, what did I pick? I picked number 6, so that's me. Then the other player picked 2. And I can play tic-tac-toe. So, and then I picked what I was saying, number 9. And if I will play with you, I can kind of see what's going on. Obviously, if you know the rules for tic-tac-toe, it's a relatively simple game. If you know how to play it, you can never lose. And you can win if the other player doesn't know how to play. So it's kind of a boring game otherwise. If both people know how to play, it's just gonna always be a tie. But the idea here is that's all I need. Just the structure, it helps my visual system understand the lines. So I understand that, I could, if this other player gets something like an 8, I can kind of quickly see that I need to get the 5, and I probably won at this point. I have two choices. They can block me here, and then I can do it right there. So the visual part is just lines and nothing more. It kind of helps us think about this problem, about the game. And then the other thing that helps quite a lot is the markings, the X and the O's. Without them, it'll be hard for me to remember. So, but that's how I can play that game a lot easier than trying to sum up and kind of look at all possibilities. I have 3 pieces, the other player has 3 pieces. Which one am I going to go after next, and so forth. The other solution is from an article. They published this article about logic gates are something that we use in kind of all digital CPUs. A processor will always kind of does, it works with 0 and 1s, and the basic operations that you can do on a 0 and 1 are an AND operation and an OR operation and a NOT. So you can take the 0 and flip it, becomes 1, and then AND is like logic in the English language. I can say that it's there. It's daylight outside and the temperature is 3 degrees. So that statement is false because, yes, I have a 1 because it's daylight outside if you're in Little Rock. If you're somewhere else, or you're listening to it at home later, I don't know. But right now it's daylight, but the temperature is like 50 Fahrenheit and not even Celsius. So the second statement is false, and because of that, my entire statement is false because I kind of linked it with AND. If I would have put OR, they say it's daylight outside, or the temperature is 3. That would have been true because one of them, it's one or the other. So that's kind of how it works here. So this is an OR, so you can see a 0 and a 0. It's a 0 and then 1 0. They don't have all of them, all the combination, but there's only 4 combinations: 0 0, 1 0, 0 1, and 1 1 for these gates. So how does this work? They use our visual system and our 3D perception. Obviously, this is a 2-dimensional screen that we're looking at, no matter where. So basically, they say we use these wires, and we have a 1. If you're going to look at 1, it appears to me that it's going, if I go from top to bottom, that it goes into the screen. It goes inside the screen. It's kind of, it starts from outside and goes into the screen. So the direction would be, not that way. It's kind of hard to move the mouse. Kind of this direction in 3D, in the Z space. And then the 0, it comes like it's coming out of the screen. If I kind of start from here is inside and here it's going to be outside. It's coming towards us as we kind of look down. Again, it's a 3D perspective. Well, and these guys went and studied it, and they said, oh, you know what? People can visually estimate these. And more complex things, not only. And notice how 0 and 0 appears like a 0, like it's coming out of the screen. They ran some user studies with more complex things, like they were combining AND and ORs together. And that's kind of, a processor would have probably thousands, if not millions, of these gates inside of it. And kind of try to understand how they work to estimate them. So they said it was easier for people to do this visually without even knowing what the meaning of AND and OR is. You can also do it by hand and figure out what the end result of that is, they said that works. So it's just our visual system by itself picking out the 3D representation. I don't know how well it works, but they have, like I said, they support that by some experiments with people, and they said that they're able to compute these things visually without our brain having to do any kind of computation. Think of what is 1 and 1, what is 1 and 0, and so forth. So those are two things. So one of them really taking advantage of our visual system, 3D perception. The other one is more of our structure in the visual system. We like to see things ordered information. So for tic-tac-toe, why is it easier to play it? Does it make us smarter? Obviously, one thing is, it doesn't make us smarter, but what happens is we can use our previous experience. So I know the rules for tic-tac-toe, and I can apply them in here, in playing the number game. So that's kind of what makes us smarter. The other thing that kind of works is the fact that it's easier for us to look at diagonals, rows, and columns, instead of doing addition. How much is 8 plus 2 plus 4? Is that enough? You know, what else do I need? So trying to do addition in our head, and maybe with subtraction sometimes, because you have to, the other player has an 8 and a 4. What do I do? 15 minus 8 minus 4 is whatever, 3. So it's easier to just look at tic-tac-toe and play it really fast rather than do addition and subtraction. So it makes us smarter. Well, it'll help us process a little bit better. It's almost like an external processing tool there. Same thing with the logic gates. And then the interactivity. The fact that I can write down the X and O's, it helps me having to remember. And always kind of, it's really easy to see at a glance. I just have to look at it half a second, and I know what the status of the game is, rather than look at those numbers, my numbers and players' numbers, what is left on the board. This way, what's left is whatever, there's no mark for it. The other players are the O's, my things are the X's. So in that case, I don't have to remember information. The next one, I'm just, again, critical thinking a little bit. Visualization is not good for everything, and actually, it's not the only solution for some things. There are other solutions than just visualization. But here is, and I think that was mathematicians had this problem maybe for a little while. I mean, for a fraction of a second. It's not a very complex problem once you know the solution. But you know, if I have a chessboard and somebody cuts off these corners, the question is, can I cover it by dominoes? So a domino is like, it's here. Can I put dominoes? I have an infinite number of dominoes. And can I start covering and kind of putting and covering? And they have exactly the same size as my squares. So can I start putting dominoes this way? And can I cover that chess piece completely? Obviously, I cannot have them overlap on domino on top of each other. They all need to be flat on the board. Is it possible to cover? So trying to kind of work it out mathematically, looking at this, you know, maybe not the best way. There is a visual solution for it. Here is a chessboard. Here is what I cut out. And then no matter how I place a domino on the board, it's going to cover what? A white and a black. So when I started, there were, you know, white and, but when I took it out, I took out 2 white cells. two white, not cells, but I guess they're squares. So I took two white squares. So you can see now that it's impossible to cover it because there's not, right now, there's not the same numbers of black and white. Like I said, this was a mathematical problem for a millisecond. They extended it to, can I have another number? So I don't know. What if there's 9 of them? Maybe in that case, I can cover it. If I have a 9 by 9, I don't know. I'll have to draw it. But if I have a 9 by 9, it's possible that I can cover it if I cut one white and one black. At least it's not. But this one clearly tells me it's not possible for an 8 by 8 chessboard. Here is a non-visual solution. Okay, so I'll read through it, but many years ago, in a proper village in the Midwest, there were 32 bachelors and 32 unmarried women. That's 64 pieces on the board, black and white. So there was a village matchmaker who always succeeded in arranging. So everybody was happy because everybody would gonna get their match. That's the dominoes in the previous solution. But one drunken Saturday night, 2 bachelors stabbed each other and died. Can that matchmaker succeed now? No. It's impossible, whatever he's doing. Again, I'm being a little bit critical, so visualization is not the only way to solve problems, and sometimes may not be the best way to solve problems. It works for some things, it doesn't work for others. So take this with a grain of salt. This entire class, it's not, we're talking about the best things to analyze and look at problems, but sometimes there's other tools out there. There's very powerful mathematical formulations that you can use. Integration, derivation, that have a lot of power, and inside of them, I don't know. Sometimes it's even hard to show things like those visually. You could, but it's hard to find the best visual representation for some things, while mathematically it's kind of, yeah, if you know a little bit of the background, it's like, oh yeah, it's obviously there. So what is kind of information visualization? Again, definition is a picture is worth 1,000 words. And I read a paper once. It was a lady who worked in a visualization researcher, but she started the paper. Everybody says a picture is worth 1,000 words. But if that's the case, have you ever seen this concept represented visually, that a picture is worth 1,000 words? But yeah, like I said, not all visualizations are pictures. I kind of gave you an example of a tic-tac-toe. It's not necessarily. Sometimes a good structure, it's the structure of the space that gives me the power there. Others are pictures, so it works either way. So sometimes we visualize, we form an image, and maybe that's kind of how the tic-tac-toe, I use previous experience. I know how to play tic-tac-toe, and I can apply it to a different thing. To remember as if actually seeing. And then Jacques Bertin, he said that visualization sometimes augment our natural intelligence. It basically uses artificial memory. In other words, to put it, you can read that. It works like an external hard drive for us. Here is kind of another way to kind of the same things. So visualization amplifies our cognitive ability, our CP, our brains. How? Sometimes it helps us simplify information and remember it. There's a whole, psychologists talk about, visual learners. There are visual learners, there are other types of learners. There are people who learn visually. If you see something, they remember it and they understand it. But in this case, if I consider a trip here and I want to go from Westminster to whatever, let me pick some that I can actually read. I think it's Hell. Well, Tottenham. So if I go from Westminster to Tottenham, I can look on the map and I see I can either get gray and red, and then, or I can get green and yellow and then black. It'll take me there. So that's, I can remember visually. It helps me. And then once I start my journey, I can always remember what I've taken and what choices do I have. So I don't have to have the map in front of me all the time, although in Saba you probably have it. But even if I don't have it, I will still remember what I have to do a little bit easier. So that's the idea of cognitive maps. Again, psychologists, well, I actually didn't tell you that, but visualization lies at the intersection between human and machine. So it's a soft science. I think I told you that. It's like software engineering, people how to code. There are no hard rules or anything like that. So again, some psychologists consider visualization as helping people. They basically say we don't remember pictures, we remember some sort of cognitive map. We simplify whatever we remember. They run all these kinds of experiments and say, oh, you don't remember this detail in a picture, although it was important and so forth. So it may be a way, we remember to simplify information. And then, like Bertrand was saying, external cognition. One thing is our external hard drive. It can function as an external hard drive. Here is another example. Marking X and O's on a tic-tac-toe is an example, but I can give you another one. I think most of us would be able to multiply 378 times 218 in our head. But it will take a while. You have to remember those partial results. Yes, I'm not saying do it, but if you have to, if you're in underground in a dark cave and you have to multiply that to get out, you will eventually do it. It may take you a lot longer. It may take you 5 minutes. You may make more errors, but we can do it. But the fact that I take pen and paper, I was telling you the power of paper, and I just write down the intermediary results so I don't have to remember them, I can do it a lot faster. So that's what I meant, an external hard drive. That's an example of an external hard drive. There are things I can remember, I could remember, but I don't want, it's not easy. Not as humans, it's not something we process numbers that easily. And the other thing, we can use the power of our brain without, like the visual logic gates. We can use our 3D interpretation or color interpretation, or thing like that. So there are things that don't even require any brain power. It just all happens in the visual system without us knowing or being able to. With the multiplication, you can always change it, the way you do multiplication, the way you remember addition, but because that's what I mean by cognitive system, is our conscious processing thing. But with the visual 3D gates, it's not a conscious thing. You just look at it and whatever feels like it's just coming out, it's going in. It's not, the more you analyze it, the worse it gets, because then you kind of start to get confused on that. So if you do it consciously, maybe it doesn't work that well. So it can work through the visual system and get processed that way in some cases. So that's kind of, and I think let's leave it like that. We're out of time actually. And so we'll pick it up on Wednesday.